Okay, good. I will now share my screen. Yeah, I hope it is visible.
Yes, sir.
Okay. Okay. So this week we have received a few queries, and these persons are notified by email. And just now I saw that there is an anonymous query, and there is no way to communicate with whoever has raised that query. And it seems that the query is not of, I would say, general interest. So I would suggest that I cannot do anything about that query. So don't send anonymous queries. Anyway, so yeah, it's now 70 plus. Anyway, I think we start without delaying further. Yeah, so the first example is just a do it yourself kind of thing. So I am just defining an operation on this set. R star is the set of all non-zero real numbers. R is the set of all real numbers. So I am taking pairs of these elements. The first one is non-zero, the second one may be zero, zero or non-zero, whatever, and I am defining it like this. This pair multiplied or whatever, this operation applied on the, when applied on to these two pairs, this gives me this pair AC and BC plus D. Okay. Now prove that this gives me a group, and you have to also show that this is not abelian, that is not commutative. So I don't think there is much to discuss here. So one by one, let us look at the satisfying of all the group axioms. So what should I start with?
Closure.
Closure, okay. The first one is closure. So what to check here? If A is a non-zero real number, C is a non-zero real number, their product is also a non-zero real number. B and D are real numbers. So, and C is also a real number, non-zero, but we do not require this BC plus D to be non-zero. Okay, so this is clear. Only thing I have to ensure that this first component is never getting equal to 0. Okay, then the next one,
Associativity.
associativity. So let us check. So what is A comma B, operation C comma D, operation, let's take another pair, E comma F. So this is AC, BC plus D, EF. This will become ACE, and this times this plus this. So that will be BCE plus DE plus F, right? Whereas if I do it the other way, C comma D, operation E comma F, this will give me, this will be CE DE plus F. Then it will become ACE B times this quantity, which is BCE, plus this DE plus F. So this one and this one are equal. Okay, then
Identity.
Identity. So what is the identity in this group?
1, 0.
1, 0. Let us see. 1, 0. So this will become A times 1, A. B times 1 plus 0, B. And 1, 0 compose or whatever. This operation will be 1 times A. So this is A. 0 times A plus B. So that is B. Okay. So this is 1, 0 is the identity. Finally, I have to find inverse of every element. So,
Sir?
Yeah, tell.
Sir, what will happen if this identity does not commute?
Actually, it's not a difficult thing, but you can see that identity always commutes. It has to. So a left identity has to be a right identity, a right identity has to be a left identity, and things like that. But this requires some, I would say, manipulations.
Sir, but in that case, sir, why do we need to write in both directions?
Yeah, actually, this is actually non-abelian. Yeah, so actually, I need to verify. Otherwise, I cannot answer this question. So this says that this is a right identity. This says that this is a left identity. Is it necessary that left and right identity must be equal? Anyway, it's a good exercise. So you think about it. Okay. So this is basically right identity. This is left identity. So in a group, if other axioms hold, like closure, associativity, are these necessarily equal in a structure? Yeah, this is a good question. So I will think about it. Okay, you also think about it. Okay, so maybe it's a good idea to do both. Okay. So likewise, you can talk about left inverse, right inverse. So let us do both. Okay, so what is the inverse of A, comma B?
1 by A, comma minus B by A.
1 by A, yes, it has to be. And then
Minus B by A.
minus B by A. Yeah. Now note that in order that this 1 by A or B by A, these things are defined, we need A to be non-zero. Okay, otherwise we cannot write 1 by A. So this times this is 1, it will be B by A minus B by A. So this is 1, 0. So likewise you check the right this is right inverse, left inverse you also check. Minus B by A. AB will be, anyway, this is 1. This will be minus B by A times A. So this is minus B plus B, that is 1, 0. Okay. So it satisfies all the desired axioms, closure, associativity, identity, and inverse. So this is a group. Only thing now we have to show is that it is not abelian.
Excuse me.
Yeah, tell.
Sir, in the identity, should the left and right identity be reversed? Placing them.
Oh, I wrote it wrong way, right? Okay, this is right, this is left. Yeah. Yeah, so here also this is right inverse, this is left inverse. Okay, fine. Okay, So only thing we have to show that this is not a commutative group. Okay, that is fairly straightforward, right? So this quantity is this, whereas if I multiply C D with A comma B, first component will remain the same, AC. Second component will become AD plus B. Okay, so these two expressions are different, so you can plug in some values for A, B, C, D and show that it is turning out to be these two things are unequal. Okay, so can you give me an example?
So 2,3 and 4,5. One way it is 8,17 and another way it is 8,13.
Okay. Okay, so this example is perhaps needed because otherwise they look different, but you have to show that actually they are different for some example. Okay, so do it. Okay, good. Okay, so this is just a kind of verification exercise, just to brush up your knowledge of the basic definition of groups. Okay, so this is an interesting exercise. Let G be a group, and let us say in this exercise it is multiplicatively written. So instead of using any fancy operations, I will just use multiplication. And this G has two subgroups, H and K. And there are three assertions. First of all, if I take the set theoretic intersection of H and K, that is always a subgroup. So how do you proceed? What is the condition for subgroups? In fact, closure, associativity, these things all are inherited from the master group. Okay, so you don't have to check those things, but only one thing you need to check. What is that?
Closure and inverse.
Closure and inverse. All these things can be put together in a single thing. So something like if A and B are in a subset, we just have to check whether AB inverse is in that group. Correct, right? AB inverse. Happy or not? Okay, so it suffices to check if A and B are in H intersection K, then I have to show that A times B inverse is also in this. Then how shall I proceed? This implies A and B are in H because it's in their intersection. This implies AB inverse is in H because H is given to be a subgroup. Likewise, AB are in K because it's in their intersection. So this implies AB inverse is in K because K is also a subgroup. Together, these two together will give this belongs to H intersection K. Okay, so this part is actually easy. Now, if I look at the set theoretic union of these two sets H and K, this is a subgroup if and only if either H is completely contained in K or K is completely contained in H. So how do you prove this?
So for the if part, we can say that
we can first consider that either H is completely contained in K, then H union K must be K, and K is a subgroup, therefore H union K is also a subgroup. And similarly, we can do for the other K is complete.
So the if part is trivial. H implies H union K is K, which is a subgroup. Likewise, K implies H. K content in H implies H union K is H, and H and K are given to be groups. So the only if part is something we need to settle.
So can I take A belongs to H and B belongs to K and AB inverse doesn't belong to H union K?
A H, B in K, AB inverse does not belong to this. No, what are you trying to prove?
Means there means A comma B doesn't belongs to H intersection K.
I do not exactly follow your line of thought. Okay, I will take some A in H, some B in K, then what?
I mean there is no guarantee that AB inverse will belong to H union K.
What is the only thing? It is this direction, right? H union K, you start with the assumption that H union K is a subgroup. Therefore, if I take A in H and B in K, AB inverse will have to be in H union K because this is assumed to be a subgroup.
No, means we have to prove a contradiction, right? So that would be easier.
Yeah. So yeah, of course. Contradiction is fine, but yeah, so maybe you are good start with, but what is the contradiction? So let's draw a picture. Let's say this is G. And I assume that H union K is a subgroup, but these conditions, neither of these two conditions holds. So that means H is something like this, K is something like this. Okay. H is not contained in K, K is not contained in H. Okay. So that means I can choose some A which is in H but not in K. And I can choose some B which is in K but not in H. Okay, then let us see what contradiction we can arrive at. Okay, but then A and B are both in H union K. Okay. So this is the hypothesis that this is a subgroup, but this does not hold. So we want to arrive at a contradiction. So A and B, they definitely belong to H union K, and therefore their product will also be in H union K because the hypothesis is that this is a subgroup. Then So this product is somewhere in this unit.
It will be either in H or in K. If it is in H, then we know A belongs to H and AB belongs to H. Then we can find the inverse, which should not be there in H.
Okay, good. So this means AB is in H, or AB is in K, or maybe both. This implies that H is a group. It is closed under inverse. So A inverse is in H. AB is in H. By associativity, this will become B. It should also be in H. So this is a contradiction because B is taken to be outside H. Likewise, if I work with this, I know that B is in K, therefore B inverse is in K. Therefore, AB times B inverse, which is same as A, is in K. Okay, so again, this is a contradiction. So this kind of thing cannot happen.
Sir,
Yeah, tell.
can we take an example of this contradiction? Like, suppose H union K is a subgroup of G, and suppose we take H as a whole G.
Whole G is a trivial thing, right? Because H is already in whole of G, K is already in whole of G. G is also contained in whole of G. I mean, I cannot give you an example of this because this is an impossible thing. How can I give you an example? It cannot happen.
Sir, is there any example? I mean, so that we can prove it can't happen.
How can I give you an example? How can I give you an example of something which does not happen? I do not understand.
Sir, I'm talking about example which shows it happens, so that we can prove that it does not happen.
I don't understand your query. Okay, let's say you're talking about Z plus. So consider all multiples of 2. That is a subgroup, right? The additive group. Also consider maybe I don't know what you are really asking for. Maybe let us take this example. Set of all even integers under normal plus and set of all multiples of 3. So this may be my H, this may be my K. So we have to show that H union K is not a subgroup because there are multiples of 2 which are not multiples of 3. This condition is not satisfied. Likewise, there are multiples of 3 that are not multiples of 2. 3 itself, for example. This condition is also not satisfied. But then, if I take the union, this is not going to be a subgroup. Why? Why is their union not a subgroup?
So 2 plus 3 equals 5 and 5 is not in the...
Yeah. 2 plus 3 is 5 and 5 is neither a multiple of 2 nor a multiple of 3. So H union K is not closed under plus. Okay, I don't know whether this example satisfies you.
So, but here we have multiplicative.
No. Whatever is the operation, these operations may be written additively, doesn't matter. Okay. So I can port this plus to a dot operation anywhere. That's not a difficult issue.
Okay, sir.
Okay. Multiplicative is just for, fixing the operation. So instead of, if I used an additive group, I have to write it as a plus b, and my inverse I have to write as minus a. Then this becomes minus a plus b equal to b is in h, that kind of stuff. Okay, this is just for fixing the operation, or otherwise I have to keep on doing things like this. Dot, star, something, some fancy operation. Okay, anyway. Okay, so this is the final part. When I say hk, again, in the multiplicative setting, hk, otherwise if it is an additive group, I would have written h plus k. So I take an element h in h and an element k in k, multiply them following the group law, and I collect all such products. Okay, and I call this set hk. Likewise, we can define kh. Okay. Now prove that hk is a subgroup of G if and only if hk is equal to kh. Okay, so which one is easier in this case? Easier things first. Only if part is easier here. Assume that hk is a subgroup, then you have to show that hk is equal to kh. Yeah, no suggestion?
So we'll take A belongs to HK and A doesn't belongs to KH and prove disprove it. Means prove that it is not correct.
Do that. You can do that. Yeah, you can do that, but maybe this is, since I'm running out of time, maybe this is slightly.
Sir, can we do something like hk whole inverse exists? So k inverse h inverse exists.
Yeah, so that's I would say a more I would say stylistic proof. First of all, we start with this assertion. Because hk is a subgroup, it is closed under inverse. And as I said, these two things are equal. Okay, so if I take element-wise inverse, I will find it in hk, and conversely. Okay, so as I said, these two things are equal. Now, what are the elements of this hk inverse? So they are of the form small hk whole inverse. So that is k inverse h inverse. Okay. So this set will be of the form K inverse, H inverse, H in H, K in K. Okay. So I can write it as K inverse, H inverse, and also HK are subgroups. So K inverse is K, H inverse is H. Okay, so you can also, go ahead and check it manually, assuming that something belongs to KH, but not in HK or the opposite, something. You can do that. What about this? So it is given that HK is equal to KH. And I have taken some A, comma B in this common set. Okay, this is basically the same set. To prove that AB inverse is in this common set. Then I am done, right? So
Sir, A is in HK, so A can be written as H1K1, and
good.
B is in KH, so it can be written as K2H2.
B can be written as K2H2 because it's a common set. So this is of this form, this is of this form. Then what is AB inverse? H1K1, K2H2 inverse anyway, it doesn't matter. So I could have taken this also as H2K2. Does that simplify it a little bit? Now this will be of the form H1, K1, H2 inverse, K2 inverse. We can proceed like that anyway, it doesn't matter. Okay, let us do it. Whatever you suggested, let us do it. H2 inverse, K2 inverse, right? Now let us look at this thing. This is an element of KH. But as I said, that is equal to HK. So this element I can anyway write as H3K3. Okay. So this quantity is in KH, but this is also equal to HK. So I can also write it as H3K3 for some H3 and K3. Then this simplifies to H1, H3, K1, K3, which is in HK.
Sir, it is H1, H3, K3, K2 inverse, right?
Okay. Whatever correct thing you write.
But sir,
This will be K2 inverse, right? Yeah.
okay, sir, seems got it.
Yeah. Okay. Yeah. Okay, fine. Happy, right? Okay, so I have.
Sir, can we proceed in the previous question like we can write KH equals K inverse H inverse? and then K inverse H inverse is equals to HK whole inverse.
Okay.
And since KH equals to HK, then HK whole inverse equals HK. So in this way, we can say that HK equals HK whole inverse. So HK is a subgroup.
No, it's not one way. I mean, this is not a two-way implication. So basically what it says that, okay, so it's a good point. So it suffices to show this, okay. So that means, what do I have to show? I have to show that H be a subset of G, some group G. Now that's becoming a little bit how do I write it in set form? So, okay, so it is given that H inverse is equal to H. Yeah, so that immediately does not prove that this is a subgroup. For example, if this is an additive group, okay, this is just closed under additive inverse. That doesn't mean it's closed under addition. Look at this example itself. This is not a subgroup, right? But it is closed under additive inverse. So this alone does not prove the group property. Okay. So I need to prove something like this. Both inverse is involved and also the operation is involved. Agree?
Yes. Okay.
Okay. So this does not imply, this does not alone imply H is a subgroup. Yeah, it's a good and important concept. Yeah, tell. What was the next question?
So what is the importance of K equals to HK in writing this step? It's writing the step of H3 K3.
No. So this is of the form. You're taking an element in K. You are taking an element in H. So it's naturally a member of KH, but the hypothesis is that this is same as HK. Okay. So yes, I can write this element also as something like H3K3.
Means if we use the associative property, then we can. Oh, sorry, it was commutative. Understood.
It's a commutative thing, yes. But this K1 and H2 inverse need not commute with themselves. Okay. But because of this set theoretic equality, I can find some H3K3. Such that this thing happens. Okay. Okay, maybe we just have a time for another exercise. So let G be a finite group. Okay, of course, without finite group, let us stick to finite groups. So I will just change it to this. The finite group. Then consider two elements A, B, and G, and their products AB and BA. Question is that these two elements must be of the same order. Of course, if G is a finite, if G is an abelian group, commutative group, then these two elements are the same, and therefore this order of AB is equal to the order of BA. Also, if A and B commute, even if G is non-commutative, then also if these two elements are equal, then definitely their order must be equal. Okay. So if they are not equal, but their order must be equal. So this is the assertion that you need to prove. So any suggestion?
Sir, we can assume order of AB is greater than order of BA without loss of generality, and then raise order AB to the power, raise AB to the power order BA, and that should be E.
Okay, anyway, so I will take something like this. Let's say the order of AB is H and the order of BA is K. Okay. Okay, so instead of assuming H greater than K or K greater than H, I will first try to use this. Order of AB is H. What does it imply? If I raise this to the power H, this will give me the identity and let us call it E. And once again, I am assuming this is multiplicatively written. Happy or not? Because H is the order, I have to get the identity if I raise this to the power H. Okay. Now what I do, I pre-multiply this quantity by B and post multiply this by A. I have to do a similar thing here, B, E, A. What is the left side?
BA to the power H plus 1.
To the power H plus 1. And right side? E is the identity, so this is just B, right? And in any group, cancellation always holds. So I can anyway cancel one instance of BA from both sides. And this gives me BA power H is equal to E. Now tell me what it implies. Does it immediately imply K is equal to H?
H is a multiple of K.
H is a multiple of K. This implies order divides H. Okay. But by a symmetric argument, we can show that H divides K. For that, you raise this BA whole to the power K and do a similar thing, pre-multiply by A, post-multiply by B, and do this kind of stuff. So H is a multiple of K, K is a multiple of A, so this implies they have to be equal because they are both positive. Okay. Any queries on this? If not, I just show you the next exercise. This is an important thing. Let G be a finite group. And the order of A is H for some given element A in G. Then if I raise the question, what is the order of A power K? Then this is the formula. Divide H by the GCD of HK. Okay. So this corollary is very important for this. If G is a finite cyclic group of order n, then G has exactly these many generators. Why? Because since this is a finite, because this is a cyclic group, there exists an element of order n. That is the definition of cyclic groups. And if that element is A or G, okay, A, let's say. So all the elements of G are A power 0, A power 1, A power 2, A power 3, up to A power n minus 1. Which of these things are also generators? They are generators if and only if they also have the order n. That is, the GCD has to be 1. Okay, so and the order of A is n, so this is n. So I am looking at all integers between 0 and n minus 1, both inclusive. Thus that GCD of that integer with n is equal to 1, but that is precisely the Euler-Tocient function of n, right? Okay, so this corollary is very important in number theory, but anyway, in algebra also. So how do I do this? First of all, I raise A power K to the power this quantity, H by GCD HK. This can be written as A power H whole power K by GCD HK. Happy? Now, GCD HK divides H, GCD HK also divides K, so this is an integer. And since H is the order of A, so this is E power that quantity. Sorry, this is not GCD HK. Whatever, it's an integer, so this is E, the identity. Okay, so this implies if L is the order of A power K, then L divides this quantity. We have not yet proved equality. We can only show that L divides this. Okay. But then we also have A to the...
There should be H. L divides H. L divides H upon GCD HK.
This is, oh sorry, H, correct. Sorry, H, correct. Now, I use this, A power K, L is also E. Okay. Then this will imply A power KL is equal to E. This will imply what?
KL is a multiple of H.
Okay, H divides KL. And I can take out this GCD HK from both sides. So this means H over GCD HK divides KL over GCD HK. Or maybe I write it this way. This multiplied by L. Okay, but I have taken out all common factors from H and K, by dividing by their GCD. So this quantity and this quantity are co-prime. Therefore,
H by GCD HK must divide L.
so these are co-prime. Therefore, it must be that H over GCD HK divides L. So on the one hand, I have this, on the other, I have this, so they must be equal.
Sir,
Yeah.
we cannot say this coprime thing if K is equal to the GCD of H and K. Then obviously H by GCD of H comma K will divide K by GCD H comma K will divide that. There will be a problem, right?
What is the problem?
Oh no, sorry.
Okay,
No.
anyway. Okay, so it's just perfectly 1 p.m. now by my computer's watch. Let us call it a day, and tomorrow we are having the test as usual in Google form. So similar pattern as the previous two tests and similar timing, and yeah, so this is our last meeting. And actually, I would like to say something to you, but maybe just stop this presentation and recording. And okay.